for the invitation to come here and give this talk. So this is some project that I'm working on together with Peter Marquardt and Jörg Schröder. We're trying to improve the precision of charm and bottom quark mass determinations even further. And well, given the topic of this workshop, I don't think I need to convince anyone that we want to know quark masses very precisely. But the natural question is, of course, to which end and how much precision do we want? And I think the strongest requirements come, as so often, from future E plus E minus colliders. And here I'm trying to figure out how this is it already. Okay, excellent. Yeah, it works. Thanks.
You can also switch transparencies from this. I forgot to. So you have to put this. Do you want to try to put this one here?
Okay, I'll just keep it at like that. Thanks. Okay. So anyway, so this is from the ILC. But other future linear colliders are similar in that respect, or even more aggressive. And what I'm showing here is the precision of Higgs coupling measurements to various particles here. So that's the projected uncertainty. And here are the different particles. And I want to focus here on the bottom quark, but as you can see, it's somewhat similar for the charm quark. And for the bottom quark, they aim to achieve a precision of, or claim to achieve a precision of, say, around 0.5% in the coupling measurement. And okay, this is only useful as a constraint of the standard model if we can match that precision in our prediction for the coupling. And since we know that in the standard model, the Higgs boson coupling is proportional to the particle mass, we need the particle mass, the bottom quark mass, with a precision of better than 0.5%. So that's the goal. And the natural question, follow-up question to that is, so where are we at the moment? And okay, so this is slightly tricky. So here's now our personal answer to that question. So that's a bottom quark mass determination, which is by now already more than 10 years old, but still very much alive and kicking. According to us, the bottom quark mass is at a scale of the MS bar mass at the scale of 10 GeV is given by around 3.61 GeV, with an experimental uncertainty of 10 MeV, an alpha S uncertainty, parametric uncertainty of 12 MeV, and theoretical, so perturbative uncertainty of 3 MeV, which adds up to this number. And okay, you can see that according to this, we already have, at least at this scale, we have the precision that we want. Of course, for comparing this to Higgs coupling measurements, we still have to evolve to the Higgs boson mass, so this scale to the Higgs boson mass, which introduces new uncertainties, but I don't really want to talk very much about this here. Instead, what I want to do is to, so since we did this, a number of further analyses by many people have appeared, and some of which use very similar methods, and also very similar input. And I apologize, I only want to highlight one of these here because I want to make a particular point, and that's the one by Vicent and friends, where they use essentially the same input, the same method more or less, and they arrive at the value which is, I would say, compatible within the uncertainties. But if you look at the detailed arrows, you see that they have a quite different opinion, I would say. For alpha S, this can be easily explained because, of course, the uncertainty in alpha S changed between 2009 and 2015. For the other errors, there are other reasons. And the error where the discrepancy is the largest, I would say, namely more than a factor of 3, is in this perturbative uncertainties. Now, of course, you can now start a big discussion which uncertainty is the correct one and which one you should take. Of course, everyone will be convinced that their own way of doing things is the only right one. But okay, one should keep in mind that all estimates of the perturbative uncertainties are to some degree arbitrary. It's not exactly clear what that error even means. And in my opinion, the only way to resolve this is to make this error so small that everyone can agree that it doesn't matter anymore. And that's what I want to talk about now. And for this, let's now take a few steps back and let me give you a reminder how quark masses are determined. So the canonical the canonical observable for this is the total production cross-section for heavy quark pairs at lepton collider near threshold. And since it's near the production threshold, it's highly sensitive to the value of the mass. I mean, the naive picture is, of course, if you don't have enough energy, you can't produce any quarks. If you have enough energy, you can produce quark pairs. So you just have to check at which energy point you can produce these quarks. Of course, in practice, it's much more complicated, but that's the naive, simple picture. So that's a nice feature. Another nice feature is since it's at a lepton collider, we have an experimentally clean environment, and since we're measuring a very inclusive quantity, it's also very clean in that respect. It's not only the production cross-section is not only a nice quantity from the experimental point of view, but also from the theoretical point of view. So it's not only the cross-section itself, but closely related quantities. I'm going to talk a bit more about this in a moment. But typically, we can go to very high perturbative orders, which is, of course, also very good. Then in QCD, we should always at least think about non-perturbative effects. And here, it's generally expected that for heavy enough quarks, that is top quarks, these are small enough to be neglected. For charm and bottom quarks, which this talk is about, we're unfortunately not so lucky. And then you can either try and go to some, I don't know, region in the cross-section where you think you might have small non-perturbative effects, or you have to look at specially crafted observables where you can have arguments for small non-perturbative effects, and that's such an analysis is very established analysis along these lines are sum rules, where we, according to everything that we can see at the moment, we achieve a remarkable suppression of these effects. Yeah, so let me just give you a small reminder what this is about. So as an example, again, I'm plotting the bottom pair production cross-section. By the way, I should say I'm focusing now here on bottom quarks. For charm quarks, the situation, everything I've said so far applies pretty much the same also to charm quarks. But here I'm showing the bottom production cross-section normalized in the usual way with this R ratio, so divided by the muon pair production cross-section as a function of the center of mass energy. And then we have these very nice and sharp epsilon resonances here. And then things start to become pretty messy, and you wouldn't really expect to be able to describe this in perturbation theory anymore. So what you do now is you don't look at the cross-section itself, but at moments of the cross-section. So you take this cross-section and integrate with some weight given by the center of mass energy to some power. And then you can show that via a dispersion relation, this is related to derivatives of the vacuum polarization function, or more precisely, the heavy quark contribution to the vacuum polarization function, at a vanishing external momentum. And so the vacuum polarization at vanishing external momentum is a quantity which just depends on a single scale, namely the quark mass itself. That scale is perturbative. So you expect to, have a reliable prediction of this in perturbation theory, as long as you are as long as you are close enough, so to speak, to vanishing external momentum. So as long as you don't go to too high derivatives here. So what you do then is you happily compute this in perturbation theory, and you equate that to either moments determined from the experimentally measured cross-section or moments from lattice determinations. And since your theory prediction depends on the quark mass, you can, so to speak, fit your quark mass so that this equality is fulfilled. Here in this talk, I want to look at, so you can look at different moments. Here I want to talk about so-called relativistic moments where n is small, namely of the order of 1. And then you would indeed calculate this via derivatives of the vacuum polarization function. Here 1 loop, 2 loops, 3 loops, 4 loops, and so on and so forth. What we know so far, at 3 loops, we know much more than we need. So moments are known up to the 30th moment, and we could easily compute more. But of course, that's far beyond what we would want to use in some rules. At 4 loops, I would say we know exactly as much as we need to. So we know these moments up to the 4th moment, and there are also approximate results up to the 10th moment with very small uncertainties, which these days I would even be inclined to believe in. So then the next step, what we are working on now, is to calculate the very first moment here at 5 loops. So the way we are doing this is we are using essentially a standard multi-loop calculation setup. But I would expect not everyone here is as loopy as we are. So let me try to explain this a bit, how this is set up. So I have different steps. They're color-coded. Blue means this blue means it's very simple. And the first step is indeed very simple. You generate the diagrams. There are established programs for that, for example, QGraph, what we are using. And then you get diagrams like this one and around 20,000 others. That's pretty easy and quick. The next step is already somewhat harder. when we do the derivatives and set the external momentum to 0, we end up with vacuum diagrams. And now we want to know for each diagram which topology it belongs to. And these are the 4 prototypes we have for massive 5-loop vacuum diagrams. And these lines can be either massive or massless. In total, we have 34 combinations. Okay, this you can do. Then step number 3. That's actually a series of small steps. So you insert the Feynman rules, you calculate traces, you perform derivatives, and so on and so forth. This is okay. This is also of moderate difficulty, I would say. So here you have to be a bit careful, otherwise everything blows up. But okay, it can be done. And now we're getting to the really hard steps. So the next step is to reduce. So we end up with scalar integrals at this point, which we want to reduce to a small set of so-called master integrals. And the canonical way to do this is to use integration by parts identities. And I want to give a very simple, almost trivial example here. So at one loop, we have vacuum diagrams of this type. So integrals with the propagator raised to some integer power a1. And then you can just look at the integral over the derivative of the integrand. And that's, of course, 0 here on the one hand. On the other hand, you can apply this derivative with respect to the loop momentum to everything that follows. And the first derivative here will just give you a factor of d. The second derivative applied to this denominator will raise the power of the denominator by 1 and give you 2 L squared from the inner derivative here. Then you can subtract and add mq squared here, the mass of the heavy quark, and cancel one of these denominator powers. And what you end up with is what you have here. So the original integral you have times a factor of d minus 2a1, where a1 is this numerator power, and then also the integral with the denominator power raised by 1. So you get a linear relation between integrals with different denominator powers. And okay, at one loop, everything is so simple that it's not even clear why you should go through such complicated things, but some such complicated steps. But at higher loop orders, this is essentially the only way to deal with this. So what you can do next is you insert numerical values for these denominator powers according to what you have in the expression for the moment. And then you get a linear system of equations. And for higher loop orders, this can be very large, like, I don't know, hundreds of millions of equations. And then you have to solve this. That is, you have to eliminate as many of these as possible in terms of integrals where this denominator powers are, for example, 1 or maybe 2 in some cases. Okay, and then you can express everything in terms of master integrals, and the next step is then, of course, you have to calculate these master integrals, and that's I would say essentially just as hard as the step that before. For this, we use 2 methods. So these are typically the master integrals. So integrals over denominators raised to some integer powers, typically 0 or 1. Higher powers could also appear, maybe 2 or so. And the preferred method to calculate this, and I'm going to explain this a bit in a moment, is via difference equations, which were originally conceived also like the reduction algorithm. They were also conceived by Stefano Laporta, and we have a highly optimized implementation of this. And as an, so to speak, as a fallback method, we're using sector decomposition. Okay, but before I explain this, I would just want to briefly mention the last step, of course, where you want to renormalize your results and get counterterm contributions from lower loop orders, but this is again pretty straightforward. Okay, so back to the calculation of the master integrals. So the difference equation approach works as follows. You take your master integral and raise one of the denominators to some symbolic power, let's call it x. For example, take the first one. Then you write down the integration by parts relations for this and reduce, which gives you such a coupled difference equations, and the aim is to get first order difference equations. And okay, on this side, of course, you want to reduce everything to master integrals, so to speak, with some symbolic power of x. So then you take these first order difference equations and plug in an ansatz. And that ansatz is given here by this factorial series here. And the next step is then you have to fix these. So this gives you recurrence relations in these coefficients A. And of course, you need some kind of boundary condition. So some of these have to be fixed. In order to do this, you send x to infinity, which okay, I'm just going to tell you this. This reduces this to a diagram with one loop less. So that's of course then much easier. And then you can use then you can plug in some numerical value for some large x and use the recurrence relations to go back to x equals 1, what you need in the end. So if you're interested in the details of this, you should ask Jörg, who's an expert. And the nice thing is, if and when this works, you can get very high numerical accuracy here. But it's not entirely trivial. So for more complicated integrals, we also use a second approach. Okay, we use it anyway for cross checks, but this is pretty, I would say these days, pretty standard. They're very nice and user-friendly programs for sector decomposition. And essentially what you want to do there, you want to reduce, you want to take your original Feynman integral and rewrite it in terms of an integral over a hypercube, which you can then perform numerically. That's, I would say, the very rough idea. And to do this, you first introduce Feynman parameters in the usual way. So you have one Feynman parameter for each denominator here. You have the usual delta function constraining these. And then you have these so-called Feynman graph polynomials, U and F. So these are polynomials in the Feynman parameters to some power. I think I haven't, yeah. And alpha here is the sum of these denominator powers. Right. And this power also depends on your space-time dimension. Okay, so as I said, we want to go to an integral of an hypercube, and to do this, you perform what's called a primary sector decomposition. And that works as follows. You look at the at the integration region, at the part of this integration region where one of the Feynman parameters, say x1, is larger than all other Feynman parameters. So you pick the region where x1 is large, and then you rescale all other Feynman parameters so that they're now fractions of the largest one. So all others then go from, all other integrations then go from 0 to 1. So you do this for the first Feynman parameter, then for the second, you identify the region where the second Feynman parameter is the largest one, rescale all other Feynman parameters, and so on and so forth. You do this for all possible combinations. That is, okay, in any given point in your integration region, one of the Feynman parameters obviously has to be the largest one. So you end up with n possible choices, and this gives you n possible primary sectors. And then, well, I'll just sketch this very briefly. There's a lot that could be said afterwards. So then you have indeed integrals over hypercubes. But you can't really evaluate them numerically because these powers here still depend on your space-time dimension, and you can't easily expand this because these polynomials can have zeros for vanishing. And it can be shown that at least in the Euclidean region, which we are considering here, all of these zeros happen when one or more of the Feynman parameters vanish. And so what you do there is an iterative sector decomposition. So you look at subspaces where these polynomials vanish for a subset of vanishing Feynman parameters. So for example, say we have a 0 for T1 and T2 equals 0. And the integration region looks like this. So T1 can go from 0 to 1, T2 can go from 0 to 1. As we did before, we identify the two possible regions where one of the Feynman parameter is larger than the other one. So in sector 1, T1 is larger than T2. In sector 2, T2 is larger. And we split the integral and rescale the smaller parameter into a fraction of the larger one. So in sector 1, we would replace T2 by some T2 tilde times T1, and similar for the second sector. And this you have to iterate until you get rid of all zeros in these polynomials. And that's actually the hard part about sector decomposition, choosing a strategy which, first of all, terminates, and second, gives you a number of sectors which is as small as possible. But fortunately, we don't really have to deal with this. This is implemented in public programs like PyZectic or Fiesta. Okay, very well. So, sorry, I forgot to say now that the zeros are gone away. You can expand around 4 space-time dimensions and then integrate numerically. Okay, so this is what we use to calculate the master integrals. And the disadvantage towards the recurrence relations I talked about previously is that typically the numerical precision is not very high, so we don't want to do this for too many of the integrals. Okay, so now let me show you some preliminary results. So this is the first moment. We can classify different contributions according to the number of closed fermion loops we have in the diagrams. The more loops, the easier. So NH is the number of closed heavy quark loops, and NL is the number of light quark loops. And of course, we always have at least one heavy quark loop, and we can have up to 4 and up to 3 light quark loops. And with a maximum number of fermion loops, this is pretty simple, so that's in blue. And we do know all contributions by now. And we're now working on this second diagonal here with 2 closed quark loops. So far, we have 12 master integrals, which don't factorize into lower loop ones, which I've depicted here. And plugging in the numerical values for them gives us this first result for the 5-loop contribution to the first moment. So here is the NI cube contributions. CF, TF, CA are the usual QCD color factors. And so this first line here plus this is from 3 closed quark loops. Here we have, I'm showing 2 significant digits, and here is the one term we have with 2 closed light quark loops and a heavy quark loop. And showing 1 significant digits. We see the numbers are of the order of 1, which is what we would also expect from our experience at lower loop orders. All right, so this brings me already to my conclusion. Some rules are, I would say, a canonical way to go for high precision quark mass determinations. What we're trying to do here is we want to eliminate the remaining perturbative uncertainty, and I've shown you first results of our for-loop calculation. So I think I'm already done, so thank you very much.
Andreas, let me just say that if you want your question to be recorded, you should use the microphone. It's a bit annoying to do this, but principal questions.
So thank you for your talk. And I would like to know, so you call this sum rules, do you use no non-perturbative correction at all? So there's no condensate in these calculations?
Well, we at the moment I'm just talking about the perturbative part. Of course, when doing the final determination, you do want to include condensate corrections, at least for the charm quark. For the charm quark, the non-perturbative uncertainty is assumed to be around 1 MeV, say. For the bottom quark, it's pretty much negligible, at least for these relativistic moments.
Okay, thank you.
So just looking at the plot of the R ratio, it's kind of interesting, or it's not completely obvious, at least to me, that you could get the moments up to sub% precision, which what you need to get to the target precision BMA. So is there a consensus in the community that from the given experimental data, you can get the moments with sub% precision?
Well, I mean, as I showed you initially,
I mean, you're still in the resonant region in some sense, right? You have 5S, 6S.
Yeah. So we do have an experimental uncertainty, and this experimental uncertainty is significant in any case. So the reason I think, Vicente, please correct me if I'm wrong. I think the reason why these 2 estimates for the experimental uncertainties are not quite the same is that there is also for the large energy region, there is a mismatch between the experimental and the perturbative prediction, and you can. It's not quite clear where you should assign that error and which area you should assign to that. But these 10 MeV we have is from, uncertainty essentially I think it was dominated by the epsilon 1s resonance.
Mhm.
So your last comment connects very well with my question. So here, as you said, you are dominated by the continuum because perturbation theory has not really set in by the time that Babar data has finished. But one way to dump this is using the second moment, not the first. So your computation is great, but maybe n equals 2 for bottom. It's a lot more relevant.
I think what we are taking is actually the second moment.
Yeah, but you're computing the first one for 5 loops.
Well, the reason why we are computing the first moment is that
easier.
the second moment is much harder. So,
I understand that.
Once we can calculate the first moment, which is some point in the future, we will also try to calculate the second moment afterwards.
We appreciate your efforts, of course. But since you presented everything for the bottom, I was a bit surprised that you're motivating things from the bottom. While
Yes.
But okay,
for no particular reason, yes. One could do the same motivation for the charm quark, and there I agree the first moment somehow makes more sense. On the one hand, on the other hand, okay, we can also argue about this for ages, but I have so from my point of view, I would say that the precision challenge is bigger for the bottom quark. I would say for the charm quark, we are already closer to what we need. But okay.
Yes. So if I may have a second quick question. So when you discuss these two numerical methods, there's also the third one, which is Mellin-Barnes. That because I think it's easy to get precision there as well. I mean, I think once you get to work, you get more digits than with sector decomposition. But
well, if you manage to get a low-dimensional Mellin-Barnes representation, I somehow doubt it. Please feel welcome to try.
Andreas, can I ask you, what's the time scale for this? You said some point in the future. Can you estimate? I know you only know when you start, but...
So we started with this project essentially after the calculation of the 5-loop beta function. That was about 2 years ago. And okay. Let's put it like that. It will still take quite some time, and I'm very reluctant to ask Peter for estimates because I won't get any answer anyway.
And I assume that in your estimate of the theoretical error, the fifth loop is the end of it, in the sense that you mentioned that you wanted to have a very small theoretical uncertainty that everyone would agree is small enough. Is this the end for the n equals 1 at least, or?
That's what I would assume. Yes, I think what should also be looked into at that kind of precision is charm quark mass effects, at least QED effects, and so on and so forth, which are also of the order of 1 or 2 MeV. But yeah,
very much smaller than the others, right?
The uncertainties, yeah, and you can include them. I mean, you don't have to treat them as an uncertainty.
Just out of curiosity, the disconnected heavy quark loop contributions to the light quark part of the spectrum, are those numerically negligible or estimated in some way?
I think what you're talking about is what we, in our perturbative approach, would call singlet contributions, right? So at 3 loops, they vanish. At 4 loops, we know that they're very small. And okay, at 5 loops, we'll see what happens.
just a curiosity. At some point, you used an ansatz in order to solve the difference equations. What tells you that the answer that ansatz is a reliable representation? Do you have any convergence of the approximation?
That depends very much on the integral in question. So for the massive tadpoles that we're looking at, I think it's more or less an empirical statement that these factorial series converge with the values of the coefficients you get out in the end. Let me go to.
The one before, yeah.
Yeah. So.
If we don't have another question, I think we're going to have a coffee break now. It's 20 minutes coffee break, and later we go on with 2 other talks. So see you in 20 minutes here.